Hello everybody, in this video we are going to solve another problem live from LeetCode's top interview 150 problem list. So far we have solved all the problems up to threesome. If you haven't checked out my videos on those problems, please feel free to check them out. Today we will pick the next one. Sorry, I opened it in a new window instead of a new tab, so let me drag it here. Today we are going to look at the next one, which is minimum size subarray sum. It's a problem of medium difficulty. Let's read the problem and make sure we understand the details. Given an array of positive integers nums and a positive integer target, return the minimal length of a subarray whose sum is greater or equal to target. Okay, if there is no such subarray, return 0 instead. So I think, yeah, I understand the problem. Let's just look at a couple of examples and make sure I understood it, correctly. So the first example is target is 7 and the nums array is 2, 3, 1, 2, 4, 3. One thing I noticed is the arrays of positive integers, so there cannot be 0 or negative in here. And the target is also a positive integer, which means the target cannot be 0 or negative either. Okay. Return the minimal integer. Yeah, so we need to figure out the size of the smallest subarray whose sum is greater or equal to target. So in this case, 4, 4, 3, which is a subarray of size 2, equals to target. It could be more, like if it was 4, 4, that would still be the right answer because it says whose sum is greater than or equal to target. Okay, so that's the answer in this case is 2. There is no another way to think about it is there is no smaller subarray than size 2 which sums up to 7 or more, right, in this array. Okay, let's look at the second example. Target is 4 and the nums is 1, 4, 4. Yeah, in this case, a subarray of size 1, which is either the subarray that only contains the second element or the subarray which only contains the third element, sums up to target, which is 4 or more. And that's why the output is 1. Third example is target is 11 and nums is 1, 1, 1, 1. Okay, so in this case, yeah, basically no matter what subarray you take, the largest subarray you can take is the whole array. If you sum up everything, you still are below target, and that's why the output has to be 0. Yeah, which is basically this clause here. Okay, sounds good. I think problem is well understood. Let's look at the constraints. The target is between 1 and a billion inclusive. Okay. The length of the array is between 1 and 100,000 inclusive, and the value of each element in the array is between 1 and 10,000 inclusive. Okay, sounds good. So let's think about an approach. Well, in all such problems, and we have done quite a few on this channel, there is always a brute force approach, right? Which is you look at all the subarrays, all the possible subarrays. So brute force is look at all the possible subarrays and sum up the elements and see what is this, and keep track of the smallest size subarray, right? And we can do this by two nested loops. One is for all the left indices of the subarray, and one is for all the right indices of the subarray. And we will basically sum up, and summing up the elements can be done by keeping a running sum, so you don't need a third loop for that. And summing up the elements and figuring out, whether the sum is actually greater or equal to target, and if it is, then updating our minimum size. Since we have done such code in quite a few problems on this channel, in this video, I'm going to skip it. And yeah, if any of you are interested in me showing that how to do it, then please leave a comment in the video and on YouTube, and then I will be happy to make a video on that one. Okay, so let's try to figure out a better solution, right? So let's actually, I've been using spreadsheets for some array problems in the past on this channel, so I'm going to do that for this one as well. Let me actually take that here. Okay, so let me do the following. The indices are 0, 1, 2, 3, 4, and 5, and the values are 2, 3, 1, 2, 4, 3. 2, 3, 1, 2, 4, and 3. So those are the values. Let me just bold the indices. Okay, so these are the values. So, okay, so, well, one thing that probably immediately comes to mind is that if you look at any subarray, let's say the subarray of 3, 4, which means left index is 3, right index is 4 inclusive. Let's say the target sum was like 5 or 6, right? Which means we have achieved the target sum. In making the array bigger and checking actually doesn't really help us get a better answer, right? We already found a subarray of size 2, which sums up to target 6. Adding one more to the subarray on the right side is not going to really help. So that's one observation. And similarly, of course, adding on the left side is also not going to help. But let's say that we are considering 1, 2, 4, and the target is still 6, right? So let me actually highlight this in a different color. Okay, there you go. Let's say this is the subarray that we looked at, and we said, okay, hey, like our target is 6, the sum is 7, so sure, this is a subarray. So it does pay off to reduce the size, right, of the subarray and seeing if there is a smaller subarray that also has a sum of 6. And like depending on how we write the code, and one common way we would probably write such code is we are expanding our subarray on the right side. Like the way we would have considered the subarray 2, 4 is that we would have added element 4 to the subarray 2, 3, right? Which means this last element value 4 was just added to the subarray. In that case, then it's worth considering what if we remove the left element from the subarray, which means if we get rid of this and then just look at 2, 4, does that achieve the target, which is in this case 6? And it does. So we already saw. So it does pay off to reduce, but given that we would have just added the right element, at which point we exceeded the sum, there's no point in removing the right element. We should remove the left element from that subarray. So that kind of gives us our algorithm if you think about it, right? Which is, okay, so let me clear these guys. Yeah. And so the algorithm is, okay, let's start with the subarrays on the left side, right? So the initial subarray is defined by 0, 0, right? So actually, let me just copy this for a lot of rows. Okay, so initially, we are saying the subarray we are considering is L equal to 0 and, sorry, L equal to 0 and R equal to 0, right? That's the subarray we are considering, which means, let me highlight what that is. That is just the subarray of size 1, right? And left and right are inclusive. And we are saying, hey, and let me just write the target here. Target equal to 6 in the example I am taking, right? So we're saying, okay, hey, does that sum up to the target or more? Does it achieve the target? It doesn't. So we say, okay, let's actually expand the array on the right side, right? So we say L equal to 0 and R equal to 1. And that means these two are now getting considered. And the sum is still 5, so that still doesn't work. So we are going to say, let's expand the array, keep expanding the array on the right side. And we get this, right? And then we finally reach our target, which is 6, right? 2, 3, 1. So we say, okay, at least we found one subarray of size 3, and so far we haven't found any, so we should actually also have minimum here, but let's say minimum equal to finally 3, and so far minimum was undefined, right? Minimum was nil or something like that in the algorithm terms, m equal to nil. Okay, let me just expand this a little bit. Okay, so we found our minimum, which is 3. Okay, we say, okay, now that we have an array, what if we try to reduce it? Does it still reduce it from the left side? So we would increment lefts, and that means we have reduced our array, and m is equal to still 3, right? And which means we are now considering 3, 1. And does that sum up to target or more? It doesn't, so we don't update our minimum, right? And but now that means we are going to increment our right. We are going to increment our right. M is still equal to 3, and that means we are considering these 3 guys here. Let's do that. And then that sums up to 6, but minimum is already 3. This is size 3, so we don't have to update the minimum, but we can try a smaller one. So we say we are going to update or increment left to make the subarray smaller on the left side by 1, and that means we are considering this subarray right here, 1 comma 2, and that still doesn't, one second, let me copy paste more rows. That doesn't actually achieve the target. Let me continue this algorithm. Sorry about the highlighting, 1 second. Okay, and then we are going to say, okay, that means we are below target now, so we need to expand our array. And so we say L equal to 2, R equal to 4, minimum is still 3, right? And L equal to 2, R equal to 4 is these 3 elements, and that will exceed the target, and but that is the size of 3, so we are not going to update our minimum, but we do shrink our array from the left side, and we say what is that adding up to, and that does achieve the target of 6. And so we are going to say, oh, we found a better minimum, let's update it, and we are going to then continue shrinking. So L is equal to 4, R is also equal to 4, but now the minimum is 2. Sorry about that, minimum is 2, and which means we are only looking at 4 here, right? Which makes sense. I mean, if that was a 6, we would have found a better answer, right? But it is 4. And then we say, okay, now we are below target. So I'm just going to complete this particular example. So let's expand the right. We found a better minimum, keep it that way. And expanding right means 4 comma 3. And finally we say, oh, that also achieved the target, but our minimum is already 2. So we are not going to update it, but we are going to try shrinking the array, right, on the left side and see what happens. And by shrinking the array, we are only considering the last subarray with the last element, but that does not increase or achieve the target. So we finally return minimum, which is 2, and that's the right answer, right? Yeah, so there you go. That's our algorithm. We basically keep 2 pointers left and right, which indicates our subarray. And we keep on expanding the subarray if we haven't achieved our target on the right side. But once we have achieved our target, we keep on decrementing or making the subarray smaller by incrementing the left side and see if we are still achieving the target. And as soon as we fall below target, we again expand it on the right side, right? So that's our algorithm. Well, let's try to implement that, right? So let's see. Well, what are we doing? So before I write the loop that does that, let's see. So we are basically first doing we are keeping track of minimum count, right? Or minimum size, whatever you want to call it, minimum size of the subarray. And that is initially 0. Well, actually, it may make more sense for this to be integer.max value, but let me write the little bit more code, and then it will become more clear to me. What else? Well, we have a left and we have a right, and both start at 0, right? And then we have as running sum. We don't want to be always looping to kind of compute the sum of the subarray, so we are going to keep a running sum and adjust it as we expand or shrink the array. And initially, since our subarray is indicated by 0, 0, we should have the num start at the sum start at the value of the element at 0th index. And they've given us that the array is at least of size 1 in constraint, so this is safe to do. But otherwise, we should handle it as a special case. Okay. And now we say while left is within bounds, nums.length, and right is within bounds, right? So right is less than nums.length. And we say, okay, what do we first check? We say if we have achieved our target, which is greater or equal to target, then we are figuring out what is the size of the subarray. So sorry, that's the size. And the size of the subarray is right minus left plus 1 because it's inclusive of both right and left, right? And we say if that size is less than min size, right? If we have found a subarray which is better than our min size, then min size equal to size. And yeah, this is why I think this needs to be a bigger value to start with. Whenever we are finding minimum like this, it's probably a good idea to initialize it to the biggest possible value, right? And that is integer.max value in our case. Okay. And so we updated our best or minimum size if it was appropriate. But now what do is we basically increment left, but we have to adjust our sum for removing that left, right? So we say sum minus equals nums of left, right? Because we are removing one element from the subarray on the left side, so we are going to update our running sum to reflect that. And else, in else we say, else whatever, well, we are doing plus plus right, and we are adjusting our sum for that, right? So nums of right. Well, actually, one thing here is that we did check that right was within bounds in here, but now we have incremented right. So here's nums of right could be throwing out of bounds exception if we went below or beyond the last index. So I think we have to check that again. Yeah, yeah, that would work. And then finally we say return min size. Yeah, I would want to run through the example we have here once. So 2 3 1 2 4 3. Let's run through that. I think it works, but just to make sure. So let's actually do it here. So the array is 2 4 3. Actually 2 3 1 2 4 3. 2 3 1 2 4 3. Okay, and the target is 6. Let's say 6 because that is the example I took in my spreadsheet. Okay, so in that case, left will initially start with 0, right will initially start with 0, sum will initially start with 2, and the min sum will initially start with max value, right? So that's what this is. And then inside the loop, we have still not achieved the target. So all we are doing is we are going to update our right value to 1, and the sum will become 5. Right will get added. The nums at right index will get added to the sum, and min size is still max because we haven't really found our target. So similarly, again, the sum of 5 is less than the target. So all we do is do this, update this, and we still haven't really checked that the sum is better because that happens in the next iteration. And that's where now we say, hey, max is, it's very tricky to do this one. Max minimum size is actually going to be 3, right? Minimum size is 3. Okay. So that happened, and then we say, hey, when that happens, we are going to update our left by 1 more, remove the value of left, which was 2 from this, or subtract it, and then this is still 3, right? And so on. So I think this should work. I'm not going to have to complete this because we kind of meticulously went through an example in the spreadsheet. Let me run this and make sure it works. Okay, it did not work. Oh, I know why. Okay. So in the special case where we never achieve the target, min size is going to be integer dot max value, right? So we need a special case here. Min size equal integer dot max value. If that is the case, then we return 0. Otherwise, we return min size. Yeah, that makes sense. I declared too soon. It works. Okay, there you go. So that's good. Well, let's submit this for running it over a much bigger test suite and also to compare our performance. Okay, so we did get accepted, but it looks like we are beating very few folks in time. I mean, I wouldn't worry about it too much, although it is interesting to see why this is the case. We'll spend a few minutes on that, but when you have such an implementation which is easy to understand, implements the algorithm, I wouldn't worry about a tiny difference because our complexity is definitely as good as it can be, I think. So let's see though, let's try to see if there is some micro optimization that we can do, right? I mean, in such cases, when the complexity is the same, what we are looking for is, are there redundant things in every iteration of the loop? Not constant time things which are outside the loop are not going to generally improve our performance compared to other submissions, right? So these 3 lines here and the last line here are not a big deal. I mean, one thing I can think of is we don't need to check both left and right are be within the bounds. And the reason is because of the nature of the sum and the way we have written this, we would not be making left go beyond right, because by that time sum will become 0 and it will drop below the target even if it was above the target. So which means left will automatically stay behind or equal to right, and which means just checking that right is within bounds would work. So that's one thing that we don't have to do in every iteration of the loop. I'm not sure if I can avoid this thing very easily. I mean, let me actually just submit this one. I don't know if it will improve much, but we'll see. Okay, so there you go. So we are now beating 99.77% of folks. Okay, that's cool actually. I didn't think it will make such a big difference, and it's very possible if I submit this again, it might fall into this bucket again or might not be top of this bucket or etc. But there you go. I mean, like the such micro optimizations is what is the main difference. The algorithm stays the same. And if in real code you have those redundant checks, I don't think it is actually a big deal to have those. But yeah, just by the inherent logic of this problem, we don't need both those checks. Okay, there you go. Hopefully that was helpful. If you're liking what I'm doing on this channel, please hit that thumbs up button on the video or subscribe to the channel or both. And like I said, if you want me to implement this brute force approach as well, just for comparison's sake, I can do it in a separate video. Please leave a comment. I'll see you guys next time.